Olá, boa tarde. Agradeço a participação de todos. Estamos aqui com mais um seminário do Grupo Produto Estrela. Hoje temos a nossa professora convidada, a professora Azadeh, da Universidade Federal do Pernambuco. Vou fazer aqui a apresentação dela. A professora ela possui graduação em Física pela Universidade Bps e mestrado em Física de Alta Energia na Universidade Mazandaran. E o doutorado também em Altas Energias na Universidade Shahed Beheshti. Acredito que todas no Irã, a professora depois pode me corrigir. Ela atualmente é professora na Universidade Federal do Pernambuco e as áreas de atuação são em teoria de campos, trabalha com Soliton, Fermi Soliton nesses temas, interações de kinks, cordas cósmicas, efeito Casimir, e o efeito Casimir é a temperatura finita. Hoje a professora vai falar no seminário sobre solitons. Eu deixo com a professora. Pode começar, professora.
Obrigada, Gustavo, pela introdução. Desculpa, eu não preparei em português, eu preparei em inglês. Então, mas qualquer pergunta apareceu, a gente pode discutir em português. Só algumas palavras não sabia, então não queria. Okay. So, I will present here. Okay, let's see. Dá para ver?
Dá sim, professora.
Ok, ótimo. Então, vamos fazer assim. Okay. So I'm sorry, I switched to English. I'm going to talk about the solitons. I will focus in specific type of solitons in 1+1 dimensions, which are called kinks. And then I will focus on their perturbations and their collisions. So let's first give you some historical context that from what time they appeared, like made people interested, and then mathematically what they mean. Especially, I will focus on 1+1 dimensions. And then the two papers we have in this year, one of them published, one of them still we haven't received the result from the journal. So any suggestion, comment is welcome. So the first one, both of them is with my PhD student João Guilherme. The first one is the focus is on normal and quasi-normal modes and their effect on the isolated kink perturbations or excitations and the kink-anti-kink collision. And then still in this line of the kink-anti-kink collision, I will introduce other types of kinks that they are called long-range tail kinks, that they are long range in the sense that if you pick the kink and see the asymptotics, you see for it takes a long range to get to the asymptotic value. So they are highly interactive because they see each other in the collision for a long range. Okay, and the point here is there were a lot of papers in the literature about these long-range ones or the other type, but these long-range ones last year appeared some papers that they proved that the way to look at the system can't be the same way of the other types of kinks. So people understood that all those papers, they are somehow wrong. So we became interested to see how we can help in this line to solve the problems and study the new systems. So, about the history of Soliton, the first time it was really, of course, they were existing in nature, but the first time being observed was with an engineer, John Scott Russell, in 1834, that the event that he observed is reproduced in this photo below in the left. That he saw that when the boat stopped, it created a bump of water, and then he was on a horse, and he followed this bump for kilometers, and then he lost it in the middle of other waves. So the interesting point was that it didn't dissipate. It was stable, the shape, for a long range, like for kilometers. He could follow that. So he knew that based on the fluid dynamics ideas till that moment, it was impossible, because the waves were known, they were dissipative, so they were gradually disappearing and being spread in the fluid. So this, no one knew any theory behind this, how this could even happen. So he devoted actually many years of his life to reproduce them and understand their behavior. Actually, he understood many interesting and important behavior about these kind of waves. He recreated them in wave times and studied, and he understood that they are like isolated bumps that while they move, they don't change shape, and their shape is something like second hyper shape, this bump. And then, depending on the mass of water in the beginning you have, then it could, while it is moving, it creates two or more of these bumps. And when they pass through each other, the ones that they have higher amplitude, they are faster. So, but you see that when they pass through each other after the collision, after that they reappear with the same shape that no one knew what is the explanation behind it, because no one knew this kind of system that you, after the waves colliding, then they reappear with the same shape and with the same amplitude. Then I will show you what is behind the system. Okay, then in the right I put another one that in principle it's really easy task to create this kind of waves if you have channels of almost one-dimensional, okay? Then with some perturbation, you could create this kind of waves, and when you create it for a long range, they don't change shape and they move. Okay, then after that, in 70s, 19th century, Boussinesq and Rayleigh independently, they came up with the idea of this differential equation, this u dot minus 6 u prime plus u triple prime equals 0. Then they not systematically they could solve it. It's nonlinear differential equation. At that time there was no systematic way to solve differential equations. So they, with some trying, they could see that this second hyper shape could be those waves that Russell observed and recreated in the experiments. But then their work was forgotten for 2-3 decades. After them, it was Korteweg, which was a mathematician, and De Vries, which was his PhD student. In 95, they came up again with this differential equation, but now they could systematically solve it. Okay, so because of that, this was it was a more systematic, beautiful work to solve a differential equation, and they came up with the idea that probably these explain those waves that Russell observed, but still didn't attract many physicists and mathematicians and engineers because people were not really understanding what's happening here, why the theories in fluid dynamics existing doesn't explain this. So the theory, physical theory behind it was not understood. So this is called KdV equation after the Korteweg and De Vries. that you see it is the local amplitude of water, and the dot shows the derivative in time and prime derivative in space. And obviously the middle term is the nonlinear term, and the last term is the dispersive term that was known. Okay, so then after their work, people really understood that there is some interplay between dissipative behavior and nonlinearity, that they somehow cancel out, and the wave keeps the shape, because nonlinearity somehow creates spectral broadening, and this dissipation creates temporal broadening, and time and frequency are Fourier dual of each other, right? So one of them compensates the other and creates these stable shapes. But okay, at that time was not that much known what's happening in the system. Until it's 1 century after, actually you see for a long time people really didn't pay attention to this work. It was in 1965 that it was a time that it was already possible to do some programming in computer. And Zabusky and Kruskov, they picked this differential equation. They gave as initial condition, gave like a cosine of x for that u. And then they saw that these waves, when they are with the evolution of these waves, when this cosine evolves, separates in some bumps, and then saw that the bumps that have higher amplitude, they go faster, but when they pass through each other, after a while they recover their shape. Okay, so this became really interesting. And this was the number of the bumps appearing was dependent on the initial condition you were putting, which was exactly like how much is that mass of water that you put there, the initial condition. But then it didn't matter after that. As many as you want, you created there, and then they pass through each other, and you have the same bumps after the collision. So at this point, people became really interested. They started believing in this kind of waves and trying to understand what is happening, because like, for example, you can see if you could have an initial condition that creates 2 of these bumps. And then if you go from left to right, you see the time is evolving, and then you see that the higher amplitude one gets fast to the point of lower amplitude one. When they superpose, you see there is no superposition principle as expected, because it's nonlinear system. But then after that, you see they start separating with the same shape. Okay. Then this was actually really interesting. This is something close to the result they had. And so you could see that although in the middle, when they totally superimpose, the behavior is totally nonlinear. But then after that, you see somehow is related to that superposition principle for linear systems. So somehow these kind of differential equations, nonlinear differential equations, they show some linear behavior. At this point, it became really interesting for many mathematicians and for physicists. For mathematicians, for obvious reason that how this nonlinear system could show some linear behavior. So they started to understand this kind of system, and in the middle for the physicists, what is the theory behind them? We didn't have any consistent theory with this kind of observation. Okay, so together they understood many interesting about this kind of nonlinear equations. So you can see the same thing three-dimensionally. You see the 2 waves coming, but in the middle they have they have some non-trivial behavior, but after that they separate with the same shape. So then, okay, but what they understood, the people understood, is that okay, we have 2 things: these isolated bumps that they don't change shape while moving, so they are somehow stable if they don't observe other ones. And there is other additional condition that some of them, when they collide with each other, then they pass through each other, and after a while they recover their shape. Okay, so that isolated bond that has localized energy density, finite energy, while moving it keeps the shape. They are called solitary wave because it's solitary, it's lonely. Okay, it's like a lonely pulse moving. But then if you add one more condition there, you will see that after adding that condition, that after the collision to be unchanged, created the concept of Soliton. This name came actually from that Zabusky and Cruz called in 1965. They called them Soliton. Then people understood that this last condition actually is highly restrictive condition, which is related to integrable systems. Integrable systems, they are nonlinear partial differential equations that they are the solution of this system changes to some finite number of operations and integrations, and they are in principle analytically solvable. In principle, in a mathematical way of thinking. Okay, so you have the thing behind it is that you have those many symmetries behind this kind of system that decreases the number of degrees of freedom in the system to the point that the system becomes analytically solvable, because most nonlinear differential equations that we know, they are chaotic, which means that if you know the initial condition, imagine initial position, initial velocity, still you can't find solution uniquely. You can, just to have some idea, imagine you have a robot, which is some pieces are joined. You give it like the initial position and the final position, but there are many ways to go from this initial position and final position, even if you give the initial velocity. So the solution is not unique. So this kind of behavior is non-integrable behavior. But there are few or rare partial differential nonlinear partial differential equations. This is not true anymore. They are really well behaved, and you can predict the path, what happens if you look at initial time and long time after, like what we saw about those waves. In the middle, it was a lot of nonlinear behavior, but then after that they separated as if nothing happened. So, but this is actually really tricky, these integrable systems, because, for example, in KdV equation, we have U of x, which is the elevation of water, that is locally defined. So it's a field because it has value at each spatial point. So it's a field, which means that it has infinite degrees of freedom. So for this system to be integrable, you need infinite constant of motion, or in mathematics language is infinite number of first integrals. But still, in different infinities, there could be different types of infinities. We know in physics that the infinities sometimes are not the same. Some infinity is larger than the other. So still, if you have infinite constant of motion or symmetry behind the system, is not trivial for infinite degrees of freedom to make the system integrable. So kind of predictable, okay? So, but this is the case for rare equations that I put here 3 of them. The KdV equation that I showed, the nonlinear Schrödinger equation. For example, there are these kind of waves people create. They work with in optics, for example, with dark and bright solitons. For example, that they are integrable, or sign-Gordon equation that the first time appeared for surfaces with constant negative curvatures, okay? And now we know they are even in superconductivity, in Josephson function, junction, and many of these systems, you see the same type of equation appearing, and the integrability of the system behind it is guaranteed with this equation, okay? But then I put one of the cases that is non-integrable, the phi-4 equation, which is really I put 5-4 because of being really important for many areas of physics. For example, this is many times responsible for spontaneous symmetry breaking, or what you know as Higgs mechanism in standard model. And 5-4 equation, you can show that it is the soliton coming out of it is non-integrable. So after the collision has chaotic behavior. This is exactly actually in the line of the work we did, that we worked with non-integrable system and seeing this chaotic behavior, because although mathematically the integrable system is really important and you categorize them and even you introduce kind of hierarchy of many of equations that they are somehow related, but the collision between them is completely trivial because they pass through each other and they recover the shape. But if it is non-integrable, then you don't know it's chaotic. So you should study the system to see what really happens. So this is actually the line of work of the two works that I'm going to explain. Okay, now let's see mathematics. This whole thing was a historical thing and the theory behind it, but the mathematical theory behind it, let's understand better. So for solitons in 1+1 dimension, the simplest case is one scalar field and in one spatial dimension, one time dimension. The time dimension doesn't matter because most solitons we know, most of them by far are static, so the time derivative actually goes away. For example, this one that I'm showing, the kink of this 5-4 theory is one of them, is static. And if you look at this potential, you see that the potential has two minima. Okay, these minima are called trivial minima because they are not x-dependent. Okay, so you look at the potential and see at some fixed point there are these minima, and for creating a soliton in 1+1, which is called a kink, for the kink you need at least two minima because they interpolate between the trivial minima. Okay, then you will see what they mean. For example, here, if you look at the equation of motion and there is the solution is tangent hyper, and if you look at the asymptotic values at -infinity and +infinity goes to exactly those trivial minima of the potential. So you see it's kind of interpolation between those trivial minima, which is another vacuum solution, another solution of the system. And there is the plus and minus. The plus one is called kink and minus is called anti-kink. That is just the other way around. I didn't put it because, okay, you see that plus minus in this phi, and you just need to exchange in plus and minus x, the order. Let's see here. Okay, now with these equations that we have, you can calculate the energy density of the system, which gives the second hyper shape. Okay, so the energy density is localized as expected. And then if you integrate in the whole space, you get the total energy of the system, which is called a mass of soliton or classical mass of soliton. Okay. So then the question is, these kind of solutions, you can see that here, the energy of these kind of solutions is higher than the trivial vacuum energy. Okay, if you consider the trivial vacuum energy, for example, here, if you look, the minimum are at 0, right? But the energy of this system is higher than that. Okay, so why doesn't it decay to those solutions? Because we know the least the principle of least energy, that it is always valid. Okay, so if you have another solution that is with higher energy, in principle should decay. But what does protect this system not to decay to those trivial solutions? This is actually related to the topology of the system, something called topological charge. Okay, then the topological charge has nothing to do with the Nether's theorem. It doesn't come from continuous symmetries because actually the thing behind it is spontaneous symmetry breaking. So somehow symmetry breaking contributes to this kind of charges. And this charge, if you look here, this Q is related to the value of the field at plus infinity minus the one at minus infinity, which means that this charge is just related to the behavior of the system at infinities. So because of that, it is called topological. It means that whatever shape in the middle, it doesn't matter for the system. What matters here is just the value at infinity, so topological behavior matters, okay? And if this topological charge is zero, you have the trivial case, which is non-topological, it is zero, and the non-zero ones, they give topological solitons. Actually, this has to do, like in the concept of topology, it has to do with the homotopy groups, and the Q equals zero is related to the trivial homotopy group, and the non-zero one is non-trivial homotopy group. Homotopy group is related to the vacuum manifold. Vacuum manifold is the manifold of the solutions of the system. The solutions that we saw, for example, these two trivial minima, okay, that, for example, interpolation between them gives another solution of the system. And the number of, in this case, the number of disconnected pieces of this vacuum manifold defines this homotopy group. If there is none, then gives this Q equals zero. So we will have trivial topology, which means that in this case, if you have a non-trivial shape, imagine you have a bump, which is the Q for that is zero, then this will decay to the trivial vacuum. So it will decay to that specific constant value that you have at infinity or minus infinity, because there is no topological charge here to protect the system. Okay, there is another thing related to the stability of the system. So up to this point, we saw the integrability of the system, which is when they collide, it protects the system, which comes from the number of the symmetries behind the system, okay, and somehow is related to that symmetries of Nether's theorem, the continuous symmetries. Another one is not related to Nether's theorem and continuous symmetries. It's actually related to the breaking of the symmetries, which gave this topological charge that could protect the system. So in this sense is stable. An isolated kink is stable. There is another thing behind this stability that we could check. Is called BPS, or self-duality condition. The BPS is just after the name of three people, Bogomolny, Prasad, and Sommerfeld. And this is like first order equation that solves your second order Euler-Lagrange equation. This gives the BPS condition, okay? Then, okay, you can, in 1 + 1, it is always possible to write the potential as 1/2 of W phi squared. Then this W is called superpotential because the concept came from supersymmetry, although here is irrelevant, the concept of supersymmetry. It's just a name for us, okay? So if you write it, you will see that the energy, I can just play with the equation for the energy that I had already with this redefinition of the potential. And then I get that the first part of the energy is squared. So it is always non-negative. So the minimum value of this energy is when it is zero. So then you see that when it is zero, the energy is related to the topological charge of the system. So somehow the energy of the minimum energy of the system is related to the topological charge that we saw, okay? So this whole thing, this was like how we have a soliton and how we protect them against the decay. This BPS condition and the topology was protecting isolated kink or isolated soliton in 1 + 1 dimension, and the integrability when it is when they collide. So it is in the evolution of them. Okay, then you may ask, okay, why 1 + 1 dimension matters? Because we are living in 3 + 1 dimensions. So the answer to the question is actually many systems in nature, because of the symmetries behind those systems, they turn in practice to lower dimensional system. For example, if you consider a polymer called polyacetylene, Then it has some layers of chain of these atoms, okay? And then in these kind of polymers, the electron can go from one atom site to the other, so it can go just in the horizontal direction, but can't hop to the other layer, okay? So in practice, the system turns to a one-dimensional system, right? Because it suppressed this probability of going to the top or below, so it moves in the horizontal line, so it turns actually to a one-dimensional system. And something interesting about them that you could see, this kind of solitons, actually it appears in this kind of materials. For example, the atom site can, in principle, these atoms, they oscillate around atom site because of many reasons, because of the temperature gives this agitation or 0-point motion. But then in the case of polyacetylene, it is strange because instead of oscillating around the atom site, they go a bit to the right or a bit to the left, and they oscillate around that new point, okay? And it doesn't matter to the right or to the left because the system has reflection or parity symmetry. Then the interesting point about this is called Pearl instability. The interesting, imagine some region, so the atom goes a bit to the right and starts oscillating. Let's call it our minimum the configuration A, okay? Then the other region, imagine it has, the atom goes a bit to the left and then oscillating around this new point. Let's call this new configuration B, and the border between them gives the kink if you define the dislocation of these atoms. If you show the dislocation by a field, okay, then you see that this field goes from one solution, one vacuum solution to another vacuum solution because it is in the border, okay? And then this is kind of mismatching between these two regions creates kind of kink that you see in the figure, kink or anti-kink. And then you can show that you can associate a potential quite similar to the 5-4 that we saw with two minima. So it is not actually just a mathematical model. It can happen in nature. There are many more examples. For example, the KdV equation, you could see it, you could see this KdV equation, for example, in acoustic wave on crystals or ion acoustic waves in plasmas. Then you see in many different contexts, the same differential equation appears, and you know the solution and you know the behavior of the system. So because of that, actually, it makes it more valuable what you know mathematically about the system, because really different systems, if appears the same differential equation, shows the same type of behavior. So then you categorize them and you know the future behavior. You can predict what happens to the system. Okay, so this one just I wanted to give you some idea about what a soliton is, and specifically what a soliton in 1+1 is, which is we are calling them kink and anti-kink. Now, okay, this is the first work we did with my PhD student. That was, we studied the normal mode and quasi-normal mode in kink for isolated kink excitations, or for the collision between the kink and anti-kink. The normal mode, actually, I think it's more familiar for you. It's in many contexts you saw, in mechanics, in many systems you saw what is a normal mode. It is oscillational bound mode that doesn't decay, it just oscillates. So this one I'm not going to explain more, but quasi-normal mode, probably some of you are not familiar with. Quasi-normal mode is the mode that the system satisfy purely outgoing boundary condition, which means that the system leaks. So the frequency of the system is not purely real. It is a complex number the real part of it is responsible for the oscillation, and the imaginary part of it is responsible for the decay. Because imagine you have a scattering state that oscillates and at the same time decays. Okay, you saw it actually even for what is the name? This the chain that you could consider. So, but one of the most one of the original examples for that, applications for that, is for a radioactive nucleus. Okay, that nucleus forms some barrier, and because of that, it partially traps the particles, but then the barrier goes gradually down, so creates the possibility of the tunneling. Okay, so besides this oscillating behavior, because of the tunneling, it starts decaying or leaking. Okay, another example, actually the most recent one that people are interested is in the merging of the black holes, that when they calculate this gravitational wave and the quasi-normal modes, knowing this information, you can know the mass of the colliding black holes. So you see, it gives a lot of information about the system. But here, what we are interested is this concept when we have the soliton, and actually like this kind of work. I don't know more than 1-2 works in literature about this subject, and these works are numerical. So it is known that when you want numerically solve for scattering state, then the error grows exponentially. So the result of the numerical study is not that trustable. And imagine you have different really close quasi-normal modes. They are really close to each other. Then it's really difficult numerically with the error to distinguish between them. So our idea was, in the context of the soliton interaction, to see if we are able to study this kind of behavior, to see this kind of modes, quasi-normal modes, in this context, and trying to build a toy model that is possible to solve it analytically. Okay, for doing that, we knew that actually what we did was inverse engineering. We looked at the stability equation, the linear stability equation. Imagine if you have a kink and you perturb the kink a bit, and then you find the equation. You find this linear stability equation, which is Schrödinger-like equation. And then if this frequency is not completely real, if it's a complex number, then this Hamiltonian, okay, because this is not real Schrödinger equation, it's just Schrödinger-like equation. This Hamiltonian for these quasi-normal modes is not Hermitian, because the energy related to the system is complex. Because if it was Hermitian, the eigenvalue should have been real, but this is not true because we don't want it actually to be true. And the system is not normalizable, but still physically relevant. Okay, so if you do this perturbation around the static kink solution, then we find this Schrödinger equation and this second derivative of the potential here. If we could somehow put a potential for this Schrödinger equation that at first has a bound state and then gradually controlling the parameters of the system, I could create a quasi-bound state. Then we could study exactly the transition from the bound mode to the quasi-bound and study the system in this case. Okay, so this was the idea. So the simplest system we could come up with was the potential well. Okay, a potential well that you know from quantum mechanics. So we know actually it's a simple system to solve. We know all the eigen frequencies and eigen functions. And then if you create two barriers for this potential well, and if you have a mode in this region of the barrier, it starts leaking. But the point is, if this, we have two parameters controlling the size of the barrier, which is related to it encodes the information about the quasi-normal mode. So obviously, when delta gamma goes to 0 or delta L goes to infinity, we recover the potential well that we have in the left. Okay, so with this delta gamma and delta L, we could control this, going to do this transition from bound state to quasi-bound state. Okay, so this was our idea, to play with this stability potential and construct the potential here in the Lagrangian, because stability potential is the second derivative of this potential. Okay, so if I know the second derivative, maybe I'm able to build the original potential. Sorry. Okay, so this is the stability potential that you saw the figure, but here you can simply write it with these constants lambda and gamma. So then we constructed the potential in the Lagrangian, which gives the second derivative of it, gives those potentials that we had for the potential well and the potential well with two barriers. So the simplest thing we could come up with, the second derivative to be discontinuous and a constant. If the potential is second order in phi, I could do that. Okay, so we could build our potential the way that we get that stability potential. And then with the one that has the delta gamma and delta L, so has those barriers, then we impose the continuity equation at the border of these piecewise. We defined it piecewise, so in the intersection of them, we impose the continuity equation. We impose on the potential and the derivative of the potential. And besides that, to have a well-behaved kink, we imposed the Bps condition. Bps condition, remember that self-duality, which is first order equation solving the second order equation, and the minimum energy of the system is related to the topological charge. Okay, with these conditions, we could guarantee the existence of the zero mode. Okay, if we get back to this differential equation here, this H eta, this, when omega is 0, this solution of this omega equals 0 it's really simple to solve it. Okay, this is the zero mode, and it is related to the translational symmetry of the system, which means that if I pick the kink, this soliton, and I put it anywhere I want, it doesn't cost me any energy, so it is degenerate. I can put it anywhere in space. So this one, we wanted just to guarantee this exists. Okay, so those continuity equation and Bps condition guarantees that. And if the omega squared is above that, imagine above this zero mode, if there exists, actually the thing we consider is just when exists one more bound state, one omega squared above 0, which gives the bound state. Okay. This is called vibrational mode or shape mode or excitation mode. Okay, so let's get back to this. Okay, so here we guaranteed that it is reasonably well behaved, and actually then we saw that with these conditions, actually the system is really well behaved. It's behaving really close to phi-4, which is much less manufactured model. I mean, it's a model. We created a toy model and really highly manufactured, and at the end we got all the results that you get for phi-4, which is really good because we could capture a big range of kinks with these potentials that we consider. Okay, many class of models of kink, they have just this edge effect doesn't exist, because this is really manufactured model. So we put it, because of being analytically solvable, we chose it this shape. But when you pick a soliton like phi-4 or other models, it's just more smooth, the whole thing. But the general picture is quite the same. Okay, so we could capture the qualitative behavior in many solitonic models in 1+1 dimension with this characteristic. So then you see that with this condition of continuity and putting together the finding the potential, you see the system is actually nice. It doesn't show any weird shape here. Okay, the right ones, they are the solitons, and the left ones, they are the potential in the original Lagrangian. Okay, then for the potential, well, we know how to solve it for even and odd eigenfunctions for the bound states. We worked with the even one, but you could simply work with the odd one. You would lose nothing. Okay, but for the case, this was for the potential well, because we are working with the bound state. But when you put the barriers, then the system leaks, so the system is not bound anymore, is scattering solution that you need to search for. Scattering solution that, besides oscillating, it decays. Okay, so if you solve for the scattering solution, which is it is lengthy but it's really simple quantum mechanical system that you solve. Okay, then we could find the transmission and reflection coefficients for this system analytically. Let me see the time. How much time I have? Sorry. Do I have time?
Sim, você tem mais aí uns 10, 15 minutos, tá tudo de bom. Se ela precisar de um pouquinho mais.
Ok. Vou tentar. Provavelmente o segundo eu tenho que só... Eu vou falar só em forma geral, não vou entrar em detalhe. Okay. So we found the transmission and reflection coefficient in analytical form, okay, which is actually, this was the whole point here, because finding these ones numerically, actually we tested it with our system and we solved it numerically also, and we got that at some point it gives terrible result, and actually we used really trustable numerical program, but then we saw that at some point it doesn't give the correct result. It is actually not well behaved. At some point is okay, but when it comes to the point that there is a transition from bound to quasi-bound, it doesn't behave well. So with this one we have the analytical results, so we can see the graphs. Okay, so here, what is important for the quasi-normal modes is it is known that in the transmission coefficient there appears resonance, and we wanted to check that. Okay, then you see that when delta gamma is small, there is still the size of the barrier is not large enough for the system to leak, so there is no resonance. But then when you you increase the delta gamma, you see that it appears this resonance structure. So let me pass here. Okay, what is important here? The quasi-normal modes, they satisfy purely outgoing boundary condition, which means that I should get back to these scattering modes here, and I should put F1 equals 0 because it's purely outgoing. Okay, so if I do that, I can solve the system and find exactly the oscillational part of this quasi-normal mode, quasi-normal frequency, and the decaying part. The graph in the left gives the decay rate, which is, at first it is 0 because still the width of the barrier is not enough for the system to leak, then start leaking, but then you will see that I'm not going to explain the detail, but then you see that when delta gamma is really large, then the delta gamma in our system is not independent of delta L, which was the width the barrier, okay? So delta gamma large means delta L large, okay? So it means that we're getting back to the potential well. We are getting close to the potential well, so it leaks much less because it should pass through a larger barrier. Okay, then the same is true for the frequency. At first there is no leaking, so it should be close to the bound state, and at the end again it's getting back to the potential well, so it should the frequency should get back there. This dotted curve here is exactly the transition between the bound mode to quasi bound, and actually the numerical methods that we tested, at this junction, it doesn't work well. Actually, it's not trustable at all. Okay, let's look at the collision. This was the whole idea. So for the collision, the most common ansatz is called additive ansatz, which means simply you put kink solution and anti-kink solution together as in your initial condition, and you put it in the program as your initial condition, and you do this collision. Of course, this can't be analytical. The system is completely chaotic, okay? So you see that there are three scenarios that are important. One scenario is that actually first let's look at the scenario C. Scenario C is that if the initial velocity of the kink and anti-kink colliding is large enough, then the thing happening that it's really high translational energy, they simply collide and get back. They can leak some energy as radiation, but the whole thing is that they reflect. Now let's look at the scenario A. When the velocity is really small, then after the collision, they create this bound state of kink anti-kink is called baryon, but gradually loses energy and it decays. So the A scenario is annihilation, the C scenario is reflection, but there is middle scenario in between, that the velocity could be giving the scenario C or scenario A really close to each other in the velocities. So this is actually the part that it is more chaotic. You see that in this part appears fractal structure, and then like you increase a bit the velocity, or you decrease a bit and the scenario changes from A to C or the other way around. Okay, this is called resonance windows. Okay, you can see these resonance windows, which is the final velocity of the kinks colliding as a function of initial velocity. Okay, and then you see that for large velocity they just simply collide. Okay, so VF, there is no weird behavior here after 0.3. Okay, but below, for example, below 0.223, the final velocity is 0, which is the scenario of annihilation. But the middle one, you see, it is sometimes 0 for specific values of velocity. Initial velocity, it is 0. For specific ones, they reflect, and the VF, or the final velocity, is non-zero. So this is called the resonance windows. Okay, so I don't have time to go through this detail. What is important here is that we introduced another parameter in the system. We called it epsilon. Okay, epsilon equals 0 is that potential well that has that just the bound state. Okay, and then we studied this final velocity as a function of initial velocity, and we saw this resonance windows. And when you increase the epsilon, you go from the bound state to quasi bound, and each time leaks more and more energy when you increase epsilon. Okay, then you will see that this whole thing, and each of these windows you see is a multiple bounce. Okay, some of them they are like two bounce windows, some of them 3 bounce or more, but people showed that like for example for 5-4, when in next to the 2 bounce window there is there are some 3 bounce windows. Next to each 3 bounce windows, there are 4 bounce windows, and it goes to infinity. So this is exactly what you see. This, it is called self-similarity. If when you zoom in, you see the same structure again and again, like here. When you zoom, like in the first one, the box, then we zoomed it in the second one, okay? And you see this repeats itself, okay? And then when you zoom again, you see again this behavior, okay? It opens to more, to closer structure. The fractal structure is something like, you know, like in the trees, if you get a branch of a tree, and looking at the tree, they look really alike, okay? Or if you pick a cauliflower and pick a piece of it, it looks like the whole, okay? So this is called fractal structure. So when you go, you zoom in smaller and smaller scales, you see the same structure again and again. But then you see that when we look at epsilon greater than 0, the first time when we zoom, it seems that it is repeating itself. It creates more and more this kind of n-bounce windows. But then you see that at some point it will go away and it becomes completely desertish. So this shows that actually this loses the fractal structure, because when we we quantified this, we calculated the fractal dimension. For example, for epsilon equals 0, which is for the bound state, we quantified it. It is between 0.8486, and for the red ones that it is epsilon above 0. This one, each time we zoom, we will see that this grows, the dimension grows, which doesn't make sense because it means that it's losing the self-similarity. And actually, in the last one, it's quite close to 1. The dimension of a line is 1. So it means that you're losing the fractal structure. So this is the main result that normal, if you compare normal and quasi-normal modes in the collision, for example, you see that as you increase epsilon, which is as you switch on the leaking of this energy or the frequency to become complex, you see that the critical velocity, which is the velocity from that point on, they just simply reflect, which is in the first one is close to 0.3. Then you see that when we increase epsilon, it becomes larger. Like, for example, in the second one, you see it is close to 0.4, and then another epsilon higher, it becomes close to 0.467, and it goes on. So the reflection scenario needs more and more initial energy to happen, which makes sense because there is leak in the energy. So you need to give the initial energy, initial velocity you give should be high enough that after the leak, still they have enough energy to separate and reflect. And besides that, when we increase epsilon, which we go to quasi-normal modes, we lose the fractal structure and self-similarity, which was the main result here. The second one, I don't have time for that, but it's fine. Any question, comment?
Obrigado, agradeço. Ótimo seminário, professora.
Obrigada.
Foi muito bom. Vamos passar a palavra para o professor Ademir, ela sempre gosta de fazer alguns comentários. Então, o professor Ademir está com a palavra.
Bom seminário, Azadeh, muito bom. Acho que deu para o pessoal pegar aí.
Espero que deu para entender.
Sim, é um bom mapa, um bom pedagógico, muito bom mesmo. Obrigada. O inglês também bem falado devagar, aí acho que eles conseguem pegar bem também, o pessoal. Outros não, outros são. Muito bom. É legal. Eu tenho algumas dúvidas, meio, assim, algumas básicas, mas meio resolvidas, assim. Eu escrevi aqui, no kink anti-kink, os 3 cenários, Você fala que ele depende da velocidade. Essa velocidade é velocidade relativa, né?
Velocidade inicial é velocidade relativa, exato.
Sim, do choque, assim. E essa era uma dúvida que ficou assim, mas eu acho que estava meio resolvida. E, assim, para mim ainda ficou meio difuso.
Uhum.
Você consegue dar sei lá, algum physical insight sobre por que isso acontece? Assim, dá para perceber?
Sim, porque esses cenários acontecem.
Sim.
Exato. Eu não tinha tempo, eu pulei. O que acontece é chamado Energy Exchange Mechanism, ok?
Sim.
Que você tem no início, essa energia é energia de translação, ok?
Sim.
E essa energia, quando eles colidem, eles criam um estado ligado, eles ficam ligados, e eles podem armazenar energia em forma de energia excitada. Lembra a equação de perturbação de King? De Linear Stability Equation? Quando tiver ômega acima de zero, significa vai ter um estado ligado com ômega maior que zero. Isso. Quando colidem, eles podem excitar, mas isso é estado ligado, então fica aprisionado no kink e anti-kink, ok?
Sim.
E eles, então, essa energia fica armazenada nessa forma de energia, e depois, se tiver energia suficiente, eles vão devolver isso para a energia de translação. O que é? Energia de translação, ok? Desculpa. Podem devolver nessa forma. E se não tiver isso, eles começam... Porque força entre eles é atrativa, essa força entre kink e anti-kink. Se comportam tipo uma partícula e antipartícula, ok? Então, eles, se não tiver energia muito alta, eles começam a atrair, então começam aquele bouncing, ok? E pouco a pouco vão perder energia. Mas se for energia muito alta, eles podem devolver essa energia, tipo energia de reflexão, e separam. E o cenário no meio é mais complicado, é aquela forma de ressonância que no meio acontece. Porque isso é bem caótico, porque depende da velocidade, pode ser um pouco menor ou um pouco maior e muda o cenário totalmente. Então, aqui é muito mais difícil explicar bem o que está acontecendo, pode explicar só qualitativamente. Okay? Mas existe explicação, que tem alguns tunings se acontecer com velocidade inicial, eles começam a refletir. Se não tiver aquele tuning, eles vão perder energia e vão aniquilar. Okay? Isso foi a forma mais qualitativa de...
Muito bom. Me diga uma coisa, e como é que vocês... Tem algum procedimento sistemático para chegar nas soluções que vocês encontraram?
Quais soluções? Daquele colisão?
Por exemplo, são soluções enormes, analíticas.
Não, porque é caótico. Não consegue resolver analiticamente.
Não consegue.
Não consegue.
Expressões bem grandes, não tinha também?
Qual é grande?
Umas expressões de soluções bem...
mas isso é um kink isolado. Kink isolado é possível fazer, em nosso caso, foi possível perfeitamente fazer tudo analítico.
Certo.
Mas colisão não. Colisão sempre é numérico. Para sistemas não integráveis, que é o caso da gente.
Muito bom. Beleza. Vou passar aí para os outros.
Oi, Gustavo.
E para os meninos aí.
Paulo, parabéns, professora, pelo excelente seminário. Vou passar a palavra para o Gustavo. Pensei que o Gustavo estava ocupado.
Alguém tem mais alguma pergunta? Algo para falar? Não tendo, eu tenho uma pergunta, no meu caso ainda é mais simples que a do professor Ademir, que é quando você mostrou a criação lá do skink e anti-kick, você tinha um gráfico lá que lembrava o de supercondutividade, né, a quebra de simetria. Você tem...
Sim, a coisa da atrás é a mesma coisa.
Ah, sim.
Realmente, em supercondutividade, o modelo de Ginzburg-Landau é o modelo fiel 4. O modelo fiel 4 que tem quebra de simetria e vai achar o kink. Só que o kink é em maior dimensão, não é? Supercondutividade normalmente acontece não é em 1+1.
Sim, sim.
Sim, sim.
A pergunta era essa. Bem interessante. E uma outra pergunta é a dificuldade de estudar física em 1+1 dimensão. Como é essas dificuldades?
Como é o quê?
Não
Dificuldades.
entendi, desculpa.
Algumas dificuldades de estudar física em dimensões reduzidas, como essa de 1+1 dimensão.
Existe em alguns sistemas, por exemplo, em esses casos que eu mostrei, realmente 1+1 é o mais simples, ok? E realmente são importantes porque dá mais intuição. Você entende melhor o sistema e depois pode generalizar para a maior dimensão. Por exemplo, trabalhar com o kink em maior dimensão é domain wall, que é importante no contexto de cosmologia ou em matéria condensada em sistemas magnéticos, ou pode trabalhar com o monopólio magnético ou cosmic string. Assim, só a dificuldade sempre aumenta, então dificuldade aumentar, intuição diminui. Então, normalmente, 1+1 é o ponto que você entende o que está acontecendo, ok? E desculpa, eu esqueci o que foi a pergunta.
Não, é isso mesmo que você tá respondendo, era relações às dificuldades.
Mas existem alguns detalhes, eu queria dizer isso. Existem alguns detalhes que é característica de 1+1, mas não nesse contexto. Em contexto de energia de Casimir, polarização de vácuo, que tem algumas coisas que acontecem em 1+1 e não acontecem em maior dimensão. Então, tem alguns detalhes que fica diferente.
Entendi, muito obrigado.
Nada.
Então, se alguém tiver mais alguma pergunta, algum comentário.
Eduardo.
Professora, parabéns pelo seminário, por vir aqui trazer um pouquinho do conhecimento da senhora para nós, né? Eu posso até fazer o convite aqui, em nome do professor Ademir, dos outros colegas do grupo, que outros seminários virão, quando a senhora precisa trazer algo mais para a gente, outras oportunidades.